Welcome back, Chemistry Theory. Let's look at part 2 now for this EQ 3.5 section, or 3.5 section. So let's look at in a sample of lemon juice, H is equal to this. So of course we see that this is going to be a bigger number than the neutral. Remember, neutral H equals OH, which is 1.0 times 10 to the minus 7 molar. And we can see that this is a bigger number because that decimal is only 4 places to the left as opposed to 7. What's the pH? So let's take a look here. So pH equals negative log of H plus. So in our case here, the H plus is 3.8 times 10 to the minus 4. And that's going to give us 3.4. Good. B. A commonly available window cleaning solution has an OH concentration of this. So we can see that OH is bigger than the neutral one, so we can see that this is going to be basic. Whereas this is acidic. Of course lemon juice is acidic. This is going to be basic. So first of all, to figure out the pH, I need to know what H is. If I know what OH is, yes, I have the ion product equation here that we can use. So if I know OH, I can easily figure out the other one. So divided by 1.9 times 10 to the minus 6, divided by 1.9 times 10 to the minus 6, H is equal to 5.3 times 10 to the minus 9 molar. And you can see, yes, that is a smaller number than what H would be if it was neutral. So this is going to give us, this is going to tell us that it's going to be basic for sure, because OH is bigger than neutral, H is less than neutral. So if I plug that into the pH formula, let's see what I get here. Negative log of 5.3 times 10 to the minus 9. pH equals 8.3. So that is basic because it's bigger than 7. All right. Just like pH, we can have POH, which is potency of hydroxide ions. Calculated very similar. In fact, the POH, very similar. If pH is the negative log of H plus, POH is the negative log of OH minus. So like H, the molar concentration of OH minus ions in solution has a very small number as well. So for convenience, we usually express in terms of POH, which is a number in between 1 and 14. Much easier to use than the really small numbers. So we have that. And another useful relationship, pH and POH compared to each other, that number of 14 there comes into play. They add up to be 14, as we'll see in the next page. The pH and the POH values characteristic of a number of familiar solutions are shown in the table below, which is actually the next page. Notice that a change in, let's highlight this, a change in a factor of 10 causes the pH to change by 1. So that's where that I was talking about the logarithmic scale, the Richter scale. We of course know that. For example, if I'm comparing 3 to 4 to 5 on the Richter scale, an earthquake of 4 is 10 times more severe than an earthquake of 3. Same thing here, 10 times more severe. If I was to jump from here to here, an earthquake of 5 on the Richter scale is 100 times more severe than an earthquake of 3. This works very similar here. A factor of the pH scale is represented by 1 through 14. For every movement here, you get 10 times more acidic or 10 times more basic. Okay, so if you look over here, hopefully your version is a little bit better than mine. So if we look here, here's neutral. The neutral area is right here. So a pH of 7, a POH of 7, notice they add up to be, if you look at any of the pH and POH values, they add up to be 14. Add up to be 14, all of them. I'm looking at neutral, when H is 1 times 10 minus 7, OH is 1 times 10 minus 7, and the pH and POH are 7 respectively. Water is around there. Human blood is very close to there, etc. Now if I go more acidic, so by lowering the pH, remember this graph that you wrote down on here. If I lower the pH, that means more acidic. So my H gets bigger, pH gets smaller. So over here you can see the H is getting bigger, 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 bigger. pH is smaller, smaller, smaller. So getting more acidic, Human saliva, rain, black coffee, banana, tomatoes, wine, colas, lemon juice, gastric juice, etc. More acidic. So H is getting bigger, OH is getting smaller, because remember they must multiply to give you 1 times 10 to the minus 14, and then we have the relationship here. So as you can see here, acidic things tend to be things that we eat. If we look at the opposite direction, as H gets smaller and OH gets bigger, the pH gets bigger as well. Egg white, baking soda, borax, milk and magnesia, lime water, household ammonia, bleach, etc. So if you take a look here, some food items are basic, but as you go down here, you can see that a lot of like things that are used as cleaning agents tend to be basic. All right, so that's kind of a relationship between the two. One other thing here, I will attach a formula sheet here, or you'll have access to in Google Classroom or from me. It looks something like this. So it has our strength of acids and bases sheet. It has this little pH color change chart, which we'll use later. But it has this nifty little schematic here on the bottom involving, if I know the pH of something, I can figure out the H. Or if I know the pH, I can figure out POH, because we know this relationship, right? So if I know pH, I can figure what OH is. Or if I know what H is, I can figure what OH is using this formula. The pH and the POH we've discussed. What about vice versa, though? What if I knew what the POH is? I'm going to figure out OH. Well, that's where the inverse operation comes into play. So one thing I didn't show you there was if I had, let's say, pH is equal to the negative log of H. All right, so we have that. Now, if you remember logarithms, to put it in exponential form, we have the base here, which is 10. Now, first of all, let's take this negative to the other side. There we go. We'll do that first. So it's usually not written here, but there is a base of 10 here. 10 to the negative pH will equal the answer here, H plus. So that's a different form. If we knew what H is, we can figure out pH by using this. If we know what the pH is, but we want to figure out H plus, we could use this formula here. Now, if you didn't take math class about which discusses logs, I just simply have those relationships here. OH is 10 to the negative POH, and H plus is 10 to the negative pH. So you can use this schematic whenever you want. The trick is to write down what you're given and where you want to go. There may be 2 steps, and of course we could take either step. It doesn't really matter, and you can get to the area that you want to get to. All right, so you should be able to do the assignment. The assignment is kind of a fill in the chart type assignment, in which you're given one of these values and you figure out the other 3. So you can use this schematic, and again, I'll have this posted somewhere so you can grab it. All right, we'll see you again.